Hello everyone and welcome to this webinar. I am Nadine Al-Kosafi, Technical Account Manager, and today I am very pleased to welcome on the floor with me my colleague Max Binago, Technical Product Manager. Today we will talk about what's new in the NxT 4.0 version of FORGE, COLDFORM and SIMHEAT. As you know, this version has been released. And we will have today the first webinar about the new functionalities of this version. In the beginning of this webinar, we will start with a small introduction about who is Transvalor. Now I will let you know a little bit for those who are not they didn't use before the GoToWebinar platform, how it works. Then we have the orange arrow here that help you to minimize the control panel. You do not be surprised. All your microphones are off. Okay, but you can chat with us and ask all your questions in the dedicated zone. Then here in the screen, you can type your questions and all your questions will be answered at the end of this webinar during the question and answer. If we don't have the time to answer all your questions at the end of this webinar, we will answer them by email. First, I will start, like I told you, by a small introduction about who is Transvalor and how we can help you. So Transvalor is an independent editor software providing a leading-edge solution for virtual manufacturing. We are based in Sofia Antipolis in the south of France. We exist since nearly 40 years old. We supply the manufacturing industry with process simulation software that gives keys for rational engineering decision making. We provide as well engineering consultancy and services. We work in very close partnership with SIMHEAT NxT Research Laboratory. Okay, as you can see here, it is an image of the team of Transvalor. All this team is happy to work for you and to answer all your needs. Here we can see where we are located. We are lucky. We are located in the French Riviera. Then we are near Nice. We are in the south of France at Sofia Antipolis. And as well, recently we opened several subsidiaries to be near our clients to answer all their needs. Then we opened subsidiaries in United Arab, in China, in India. And as well, we have several distributors that help us to distribute all our solutions. More than 1,000 customers interest our solution. These customers are works in different sectors, for example, in energy, in aerospace, in automotive, in heavy industry, and as well, we have several academics that work in close partnership with us to integrate continuously all the innovation that comes from the research in all our products. Transvalor help you to increase your part quality, to increase your production. And for this reason, we have a platform that can help you to go from the casting till the fatigue life cycle management. We have several products that goes from the casting, for example, with StirCast. Then here we can see together a simulation of casting, of metal casting and solidification. After, we can model as well the hot and cold forging. Here we can see a video of a crankshaft forging. We can model as well the heat treatment. Where, for example, we are seeing here a video on induction heating. Then the aim of all this is to follow all the properties of the metal till the end. We have as well a solution with the welding. We can study the fatigue and the life cycle management as well with that set of product. Here we can see the fracture evolution inside the metal. We can study the microstructure on different scale. Here we can see the study a polycrystal evolution, and we can see the evolution of the grain on the micro scale. We can study the microstructure intercast, for example, during the solidification by the CAFE method. And as well, it is possible as well to study on the wall part on FORGE, for example, using GMAC model, and as well on the microstructure using DGMU. Now, I will let the floor for my colleague, Max Binago. And he will let you know more about the NxT 4.0 version.
Yes, thank you, Nadine.
Switch off my camera. Thank you.
Yeah. So hello everyone, I'm Max Binago, Technical Product Manager at Transvalor, and it's my pleasure today to present you the novelties of FORGE, COLDFORM and SIMHEAT in the version 4.0. So some of you have maybe already read the product overview or worked with the new release. So we can say that this release contains a lot of things. So many of you asked us for improvements, so we have tried to implement them in this release. So we can say that we have an exciting roadmap for the next years with so many ideas, so many improvements to do. So we will continue to make our product more efficient and really adapt it to your needs. So all the team has worked several months to achieve these results of this release. So we hope that you will enjoy working with it and that it will meet your expectation. So the first transformation that you have seen when you have opened the software, the release for the first time, is the home page. So we have redesigned the home page to bring together common action that you are doing. For example, creating a new project from a template, opening an existing project, starting one optimization, which is a new feature of this product, of this release. So typically here is the interface of FORGE 4.0. So you can see that we have organized by application the different templates. So it's directly linked to your license. So if you have a COLDFORMing license, you will have the COLDFORMing templates available. And for each categories, we have grouped, bring together all the templates. So for example, we added new templates for forming simulation. So for example, we have now flow forming simulation templates. You have also a conducting heating process, flow forming process in 2D, and you have also new templates to simulate magnetic pulse forming. So in the future, we will also add comments to each template to indicate, to show you what are the different capabilities of these templates and the different properties. So you have the same way to do with the COLDFORMing templates. So you have the store with all templates, and also for the heat treatment section, you also have templates, and you can notice that we added a new template to simulate night reading simulation. So all the tutorials are also available in this windows from the left. And one more time, if you always worked with the same template, you can add a favorite to your home page to start directly with your simulation. So here you have the recent project view, and you can also use a combination of control keyboard shortcuts with a double click on the stage to open directly the results. And with Control O, you can also browse your drive to open a simulation. And here on the right, we added this new option to start an optimization. And if you want to stay tuned with Transvalor activity, you can double click on our logo and you will go to our website, and you can go to our blog to check all the news of Transvalor. So that was the first things. Then I think that everybody who is using FORGE and other software spend a lot of time creating projects and analyzing the results. So this operation you perform are often redundant and very time consuming. So we have decided to simplify everything for you in this version. So we have developed our own API in Python. So now we give you an access to all feature in a simplified way with a Python script. So this new feature will offer you many advantages. It's time saving. You will have more automation. You will secure your project, and you will have now interconnection with other applications. So an API is a kind of interface, a library where we have defined all action that you are using in FORGE either in the setup or in the analysis mode. So you can now easily create, start, and analyze a simulation from scratch in an automate way. So you can fully automate the setup or a portion, and you can also automate some action in the analysis. So, and if you are working with several applications, you can also ask for Forge results without opening Forge with a Python script. So that's the strength of this API. So here is how it looks like, how to use this Python API. So for example, you open the first template, you want to modelize a cold forming simulation. So imagine that you have designed your process with 3 stations, and for each station you have one STL file. So here the idea will be to use a script to directly build the simulation with 3 operations and all the meshes. So here you have a new Python console where you can load a Python script. So I will load this one. As you can see, you can have some pop-ups windows, so you can interact with the user. So here I will paste the path, the folder of all the geometries. And here, as you can see, we have automatically 3 operations that has been added to our project. We took the name of each of them, and for each operation, we have imported all the dies, all the components. So you can see that in 4 seconds, you can save a lot of time by creating a project. So for example, we have imported STL file, as you can see here. So the idea now is to mesh all the components in one way. So in our distribution, you will find a lot of examples of Python scripts. So we decided to write first example to give you an overview of the capability. And here, for example, you have one which is called mesh all rigid dies with a user mesh size. So here you can give the mesh size you want for all the components, and we will mesh all the components in one way. So it's extremely fast, and you can see that there is a lot of combination. And if we look again in our folder, you will find some Python script to convert all the rigid dies to a deformable dies, for example, for a coupled simulation. And you also have the capability to create your own actions that are not yet implemented in Forge. For example, convert a deformable die to a rigid die. It doesn't exist yet, but with Python you can do it. So I will say that there is an infinite number of solutions of capabilities that you can do with the Python interface. And one more thing, you can also use this tool that is provided by Transvalor with the version 4.0, and you can directly drop some Python script. And for example, here, this is one Python script to create an entire project ready to run without opening the interface. So you just have to drag and drop it here. You run the script, and you will see that we will generate all the setup. So it's a spindle tutorial. And here, after less than 4 seconds, you have your project, which is already created and available for run. It's really, really fast. So that's concerned the setup. So I will have now some example for the analysis side. So imagine that you have run a simulation here. You switch to your analyze and you want to automate the analyze. So for example, you configure your view, you activate the symmetry, and now you can run a script to divide the view in different views and display different results at the same time. So one more time, for the post-process operation, we added some example in our distribution. So this one is multi-viewer, multi-results. And when you run it, it will add automatically different viewers with your own configuration. I mean, you can configure the scalar you want to see, the number of levels, the min max values, and so on. And now you can directly analyze your setup with more efficiency, let's say. It also works from this kind of window here. You can also run some post-processing operation without opening the interface. So for example, here is our project, and I will generate one animation and export in VTFX data the results. So you will see on the right, the VTFX data is automatically created, and then I can open it in my application to check the results. And this is also a new functionality of 4.0. You can load VTFX file where you have several results and several increments, and you can run again the animation to see the results. Here you can switch between the different results that you have exported. And for example, here the contact with only 2 levels. And maybe the last example, because the time is running. So last example of this Python API. So let's imagine that I will load a template. So if you are interested in having some custom tools dedicated to your application, to your use, to your applications, we can work together to design an interface which is very adapted to your needs. And for example, here it's a user interface made with our Python API that allow you to define all your hot rolling setup in a single confirmation, let's say. So you can create your own fields, loads the different parameter of your simulation. For example, here the mesh file for the billet, for the walls, and you can define some properties, mesh size, and so on. And then when you run the script, it will automatically build the complete setup with your own parameters. So you can see how efficient it can be, how you can increase your productivity with the Python API. And maybe one last animation here with this hot rolling process. So for people who are simulating this kind of simulation, you are always analyzing same results. So you had a cutting plane in the middle, you analyze the contact, the deformation, and the different forces and torque that you can measure on the rolls. So here with our Python API, you can directly automate this view, and you can also automate all the exports for a computing report afterwards. So another another improvements, another feature in Forge and COLDFORM and SIMHEAT 4.0 is the automatic optimization. So it's now available in the interface. So I think that it will become an essential tool for you to optimize your existing process, to improve the quality of your components, or to reduce your costs, or to identify some process parameters, for example. So here you have the 2 ways you can start an optimization, either from the home page or directly in the process tab. So here, this is how it looks like. So here we have a project. So you can either go to home and open an existing project to start an optimization, or you can go to the process tab and add one optimization in this location. First of all, when you had an optimization, go to view, yeah, you will have a new Windows here. to define the parameters. So first of all, you have a goal when you run an optimization. Do you want to minimize force? Do you want to save raw materials? Do you want to have certain values of a field in your part, and whatever it is? So it's called a minimizable. So here you can see that we had several items to define a goal. For each item, you will find all the specifications and some example of use. So for example, if you worked with initial volume of parts, it's useful when you want to reduce the flash of the final parts and to get the better input, the better initial dimension of the billet. You can also have a goal of force. You want to minimize the forging load on your press. And you can also use this kind of item, reverse engineering, to identify friction coefficients or rheological parameters in your simulation. And here we will make automatically comparison with experiments, experimental data. Then to go to the goal, to achieve the goal, you can define different variables. So here, for example, we want to minimize the force on the hopper die. So how can we do it in reality? Maybe we can change the lubricant, maybe we can change the temperature of the billets, and maybe other parameters. So here we have the list of all the parameters that can be changed for an optimization. So for example, the property of parts, you will find friction, you will find the material, initial temperature, and many others. And sometimes it's also useful, or you need to change a little bit the design of the dies to prevent any forging defect or whatever it is. So you also have this parametric modeling. So we still have this Kupplung with a CAD system. So for example, with CATIA, Creo, SolidWorks, and so on. So you can ask for a new design for each simulations that you will run with FORGE, COLDFORM, and SIMHEAT. And of course, you can have some constraints when you are changing the parameters. For example, you want to have no underfilling, no folds inside the parts, or you don't want to exceed a certain critical values of damage in the part, something like that. So you also have many capabilities here, many items that you can select to define your optimization. And as soon as you have finished to define it, you can run the simulation. So typically you will define a number of simulations that you will run, either sequential or in parallel. This is new options here to reduce computation time. You can roll several simulations in parallel for the optimization. And then at the end, we will start all the simulation and we will rank all of them from the best one to the worst one. And then you have now a new environment to analyze the results of your optimization. So this is a tab optimization. So here first you have a summary of the optimization. You will find all the parameters you have defined. And on the right, you have the list of all simulation you have run. As you can see, you have some green color, which are good simulation that respect the different constraints or rules that you have defined. And some of them are orange, which means that they are bad solutions. So here you have a results tab, which is very useful because you can sort from the best one to the worst one, all the simulation. And for the first one, for example, it gives you automatically the good parameter you need to achieve your goal. So this is the purpose of the automatic optimization. And we also took this occasion to add several improvements to this module, and especially here the main effect diagram. So here you can display all your simulation. So one single point represents a simulation. And for example, here you can see how one parameter is very important and affect the results, the answer, the results of the optimization. And for example, here we can see that we have a bigger linear regression, a bigger coefficient here for the lubricants. So maybe the lubricants play a major role in this study to minimize the forging load. Then next one, the self-radiation. So in this version, we have enriched the heat transfer model by introducing the phenomenon of self-radiation. So it's now possible to take it into account during the exchange computation. And it's very useful because you can directly see if a part has an influence on itself or on the other parts which are in the neighborhood. And in this example of 4 gears during a cooling operation, you can see on the right, with made a cutting plane, you can see that the position of other parts influence the cooling rate and the temperature inside the part. So you can now imagine that we will predict with a greater accuracy the time required to cool the parts, and also to predict microstructural evolution during this variation of temperature. So this option has been added in the property of the simulation. You can find is the radiative transfer. So this option has been added for all heat treatment templates, and also for some of the forming processes, for example, the ring rolling or baking, where you can have faces which are seeing each other on the same parts. So next functionality, next novelties, for cutting, sharing, and fine blanking processes, and maybe others, a new modelization of the ductile fracture has been developed with the aim of achieving more realistic and accurate results. So instead of deleting results that we used to do in the kill element algorithm, now we have changed the way. We are now splitting the elements in 2 elements, and it changed a lot of things. So here, this algorithm integrates a crack where you have a critical damage value, and it calculates its propagation path, and then it propagates the crack across the parts. So here you can see comparison between the old algorithm and the new one. And I don't know what do you think about it, but on the right side, it's very smooth and it gives better results for the sharing processes. So how to use it? Typically, for example, here, we have a comparison between so here on the top you have the old simulation with the old algorithm. So you can see here that we have quite not very fine mesh, I would say. We have refined the mesh where we are cutting the parts. So we have made a comparison with the same setup, same mesh size, and here on the bottom you have the new setup. So let's see how it works. So first of all, you need to define in the feature the damage. You need to activate the damage as usual, and you can select damage criteria. So the new algorithm, SIMHEAT algorithm, works for all damage criteria. So first you activate it, you define a trigger value, and then you just have to go to the property of the parts and add a user variables, which is called this one. This one should be called so in the damage criteria, you find all the new user routine we have implemented to work with phase field, the SIMHEAT algorithm. So there is several models, depends what you want to observe. Is it linked or not to the mechanics? And then you need to define also the trigger value. And when we switch to the results, you can see that we have here a better smooth. This is not the good one. Okay, it is on the top. Sorry, on the top you have the new one. So that's why, yeah, on the top you can see the difference you have between both algorithm. the kill element solution and the phase field solution here on the top. So another novelties in this version is related to the oxide scale. So we have now integrated a model that allow you to take into account the oxide scale growth during heating, but also the spalling, the break of oxide scale during forming operation. So here, one more time in the property of the part, user routine, you can select either the scale growth user variable to compute the evolution of the thickness of the scales, oxide scale. So you can select your heating mode, material type, and then we will predict the thickness of the oxide scale. And then you have another user routine, which is called the scale break, where you can activate it to see how many thickness, how many oxide scale you will lost during the forming operation. And on the right side, you have one illustration of a rolling application where we have computed this oxide scale growth. And during the rolling application, we have used the scale break user routine to compute the loss of oxide scale. So another major improvements, major novelties in this version 4.0 is the new 2D solver. I mean, we have now a much more faster and robust 2D solver. So we have managed to significantly reduce computation times on multi-bodies cases. So typically for assembly processes, die stress analysis, and other processes where you have different bodies which are meshed in volume. Hence, we have now a better stability of computations and a better convergence also. So this option of the new solver can be activated just before the run with this option optimize for 2D models. And on the right side, you can have an overview of the speed up that we obtained during our different tests conducted during our implementation phase. And for some of them, we have reduced convergency problem, so we drastically reduce computation time, and we get now very good speed up with this solver. Concerning the mesh, we have worked on a local remeshing algorithm. So typically today, today or with previous version, when you remesh parts, you remesh the entire parts, even if you have only localized deformation or not. So it can have some drawbacks concerning the diffusions of fields or the loss of volume. So here we have decided to change it and to implement this local remeshing. So we will only remesh the parts where we have degenerated elements. So we continuously analyzing the quality, and as soon as one element has a bad quality, we will remesh it and the area around. So to use it, you can go to the billet remeshing option and activate your local remeshing feature. So now for people who are simulating flow forming or spinning processes, we have developed a new simplified 2D approach, which is more faster than the conventional 3D approach. So with this new approach, you have also new kinematic files where you can pilot, you can define the movements of the roller depending on their velocity, of their position, so on. You can define the different position of the rollers. You can work with several rollers. And then this approach, of course, has a shorter computation time, but it gives relatively good approximation of the forces on the roller. And it's really easy to set up, and we get a first estimation of the thickness variation and also deformation inside the parts. Okay, now another new feature, new tools that is available in the tools section of the homepage is the material data tool. So here, it's a tool that allows you to generate material file for different applications. So as you can see, you can define cold forming properties, hot forming properties, electromagnetism properties for induction simulations, or also for heat treatments, you have also capabilities to define your properties or to view the material properties for this application. So on the right side, you can see one example of this viewer for a rheology dedicated to hot forging, where you have here different tabs where you can see the parameter of your low, you can draw your flow curves, you can access to all the properties, and you can easily manage your data now with this tool. Then we have extended with this version of Forge and the material modeling capabilities, because now we can use SIMHEAT library. So SIMHEAT library is a dynamic library that offers either basic or very sophisticated model of plasticity, viscoplasticity, and other coupled plasticity, viscoplasticity model. So to do this here, you can go to the property of your billets. You can click on create SIMHEAT material. So to use it, you need to have a license for SIMHEAT, which is a component of the ZSET program, ZSET family. And here you will be able to open the SIMHEAT interface and to build your model and to use it for a forming simulation. So another interesting tool I wanted to highlight today is Dynamics. Dynamics is a new application in the interface, and it will allow you to visualize more easily grain size evolution and recrystallization during forming operation, but also during its treatments. So typically you have a new interface where you will load your project, which has been run with Forge before, and you will define different sensor, either on a cutting plane, either on surface, whatever you want. And then you need to have one mean field solver. So Transvalor is providing a mean field solver to compute such simulation. So it's GGMU, but you can also plug your own metallurgical solver with this application. And typically on the right, you can see some results that you can obtain. So here we put two sensors on the parts, one on the surface, one at the middle. We have defined a population of grain, so in grain size distribution. And at the end, after the recrystallization process, you can see the new distribution of grain size and also the recrystallized fraction. Do we have a full recrystallization or not? So it's very interesting results. And to finish this webinar, I wanted to mention other functionalities that we have implemented either in the setup or in the analysis. So you have more even more powerful feature concerning the meshing. So we change a little bit the way we mesh the parts. So you have now a menu where you can also select meshing capability concerning the distributions. You can define mesh size by a distributions. We implemented some contour precision for 2D contour. We have improved our database, and especially concerning the presses, with new capability of simulating your own equipments. So you will find new templates of presses in the software. We also had a very useful option, such as the stop force on different dies, so you can make the sum of an effort of a force to stop your simulation. And to create geometries, we have new tools, which are the 2D CAD, where you can easily create a contour. We also have the shaped roll billet, axisymmetric billet creation tools. We added some new keyboard shortcuts to move, to rotate the parts. And we also have made some improvements for the mesh boxes. You can now rotate mesh boxes. You can use other new options to define your mesh boxes, and it will give you more flexibility, more tools. Yeah, and there is more, of course. And the last one, the analysis tools. So now you can visualize the tensor with new options. You can also move and resize the overlay plots. You have now new settings to manage the vector visualization in your simulation. You have new legend settings. You can define a number of levels. You can change the size of the legend text. You can display with scientific notation, for example. You also have a new widget, which is called picking information. So when you pick different nodes, different triangle, you can get the list of all of them and the scalar which is associated to your selection. And you can export this information for later use. We also made a lot of improvements regarding the VTFX files. So now when you export an animation in VTFX format, you can select several results you want to add in this one. As you have seen, we can run an entire VTFX file now. You have new option for the export of geometries. When you want to export an STL file of your part, you can now select different increments to export the results for later use, typically for a structural analysis. And we have now new options regarding cutting planes and so on. So if you want to have more information about the content of this version, so look at the product overview, and you can also go to our blog to get the information. So as a reminder, this is the end of the webinar. So now it's time for Q&A session. So you can type your question here and we will answer it with Nadine. So I would like to thank you for your attention. For those of you who are very interested in having more information regarding the Python API, so I invite you to register to our next webinar coming in March, which will be dedicated to the Python API. So if we have any questions, we will be happy to answer them with Nadine. Thank you.
Thank you, Max. Thank you very much. Yes, thank you, everyone. Today we have a lot of participants. We have 100 participants. We are very happy to see you today. And now we will start to answer all your questions. The first one, Max, is about concerning the oxide scale function. Is the loss of forging volume due to the oxide scale is shown in the results?
Today, not directly in the scalar results, but we have a Python script that can predict, that can compute this loss of material for the version 4.0. I think it's already in the distribution. And for the next version, we will integrate it in the scalar results, I think, yes. But you can already access to this information, yeah.
Okay. And can this result be transferred to the next stage, the loss of volume?
It's a good question. Today, we do not apply any scaling, for example, or we do not change the mesh for the other operation. It's a good idea.
But we can do it manually.
Yeah, manually you can. Yeah, you can compute the volume and so on. But we will think about a tool to transfer and to take this into account. Yes, it's a good idea.
Yes, a direct one. Yeah.
Yeah.
Thank you. Is it possible to simulate recrystallization also in stationary rolling?
Not today. We don't have any models compatible with stationary rolling. No.
There is some, I will add, yeah, because I already discussed with the developer, there is some ideas is to make it a posteriori, then after the simulation to make some a posteriori then computation on recrystallization during stationary rolling. Yes.
Yeah, typically the strategy will be to use dynamics, I think, to compute the recrystallization for steady rolling process, yeah.
Thank you, Max. There is not the time parameter, so how can static and metadynamic crystallization be managed?
To use dynamics or for this kind of simulation, we need special material files. So everything is defined in these material files. And if so, Transvalor is providing some material files for crystallization. And if you do not find your material, we can also send you one identification parameter procedure to find your own parameter for your steel alloy and so on.
Okay. Is it possible to differentiate the shear surface and the fracture surface with the new SIMHEAT algorithm?
Yes, you're right. I forgot to show it on the. Maybe if you still seeing the screen, I can show you. Yes, yes, because when you are using the new algorithm, you have new fields, and especially you have the crack surf, where you can see in red the surface where you have shearing, and above in blue it's surfaces where you have deformation in reality. So you can use this fields to highlight the shearing zone during the cutting process. Yes.
Again, on shearing, what does the new algorithm for shearing do differently? How does it work compared to the kill element?
The old algorithm is based, so both are working with damage criteria first. So first of all, you need to compute the damage criteria and to define a trigger value. And as soon as we reach one element reaches the trigger value, the old algorithm was deleting these elements to split or to cut the mesh in two bodies. And now when we reach a trigger value, we had new nodes in the elements to create an internal surface inside the elements, and then we will open the elements into bodies. So we have less problem, less issue regarding the volume loss, especially here with the new algorithm. This is the main difference. We do not delete, but we split, we divide one element in two, so we reduce the volume loss of elements.
Thank you. Can we predict, this is again the same, a little bit the same question, but then can we predict the scale formation and the scale loss during forging process? The oxide scale, yeah.
Yeah, the model is compatible for heat treatments operation as for the forming operation. As soon as you define the oxide, so the oxide scale generally appeared during heating phases, but you can also add it for forming operation, yes, to see the evolution, and yes.
Yeah, I think it is. Is it possible to analyze a reduction ratio in closed die forging?
No, a reduction ratio.
Yeah, I don't. Yeah. Yeah, we will ask the person to tell us more.
Yeah, maybe we will come back to you to get more info. I don't see any answer to this right now, but we will come back to you, Mr. Neck. Yeah.
Okay, we will be back to you. Is it possible to specify a limited volume and an ambient media in heat transfer simulation? Example, furnace chamber, heat transfer exchange between the medium and the multiple object. A limited volume of ambient medium. I think we will be back again to understand more the question, and we will answer you by email if you agree, Max. Yeah.
Yes, it's maybe related to fluid analysis. Yes, we will come back to you with answers on these topics. Yes, it's the topics we are discussing right now, and I will come back to you with more details. Yeah.
Okay. Does shearing algorithm improve cutting force prediction?
Honestly, we do not. Personally, I do not check the differences in forces. It's a good question. I have to make some tests and come back to you. Yeah, no, we do not make this study right now.
Okay. There is one I will answer. Recorded session will be shared with us. Yes, for sure. For all the participants, we will send you this videos and we will share it with you. And a last question is about, is the microstructure analysis available for titanium forging at different temperature?
Today we are quite limited with material data, and so we have few materials for titanium alloys, right, in our database. So look first at this database to see if you can find your material. but we do not have so much material for titanium alloy for microstructure evolution.
Yeah. With the new analysis tool and legend settings, can we set up custom color maps?
Yes. First you need to define your own custom legends in the interface. With the new pop-up, you define your custom legends, and then when you will write your script, you can ask for your custom legends, and then it will be automatically applied. But you need first to define your custom legend with different color or levels you want in the interface.
There is one that I will answer this one. In a simulation of heat transfer only, is it possible to run an optimization to find the curve of values of the heat transfer coefficient in order to identify a corresponding between the calculated temperature and the experimental measured temperature? Then yes, for sure, we can use the optimization model to make inverse analysis. Then you will define in your in your manufacturer part, different sensors, and we can, by reverse analysis, determine which is the best heat transfer coefficient that will fit with this experimental data. Okay. We have another one. Can 2D flow forming approach handle internal counters which are non-axisymmetrical?
No, this approach is full axisymmetric approach. So for any defect you can have, any behavior which are not fully axisymmetric, we will not be able to see them with this new model, new approach,
Okay.
basic approach of 2D.
They need to make it in 3D. Maybe.
Probably.
Yeah. Yeah, because we have this new approach that is 2D at the half, but as well we have the 3D one. Then yes, for another question on titanium. Titanium alloys may have defects like forging, shearing during forging. Is it possible to analyze such defects?
Yes, it's directly linked to a damage criteria. So in the property of the part, you can define a damage. You can ask to compute a damage criteria. So we have a list of different damages available. So need to find the one which is the most adapted to this application. But yes, we can compute it, and you can also activate the damage feature that will show you either the scalar values, the highest value, where you probably can have a damage, or you can also directly see the damage by splitting elements or deleting elements with this activation. Yes.
Thank you. So last question, because we already get to the end of this webinar. Concerning post-processing with Python API, there is a way to combine nodal and 3D element results? Then to see at the same time results that are nodal and 3D element?
Yes, there is no restrictions. You can display for example, the contact on the right and another field which is calculated on elements on the other side. There is no restriction like that. No restriction for the display, no restriction for the export, and so on. No.
Okay, we still have one more. The last. Does the Python API allow us to export 3D results? Example, temperature in 3D part in an open source format that we can use in Python with other software?
No,
yeah.
That's the main goal of our API is to be able to use Forge to export the results. Today we have different export formats, the UNFO, and the VMAP format, which is a new one. And that's the possibility you have today to export the volume results and the 3D results. And with Python, I think that we will be able to list all the results, all the nodes, all the results, and to export them in another formats. If you have a template of formats, I think that you can ask with Forge the list of all the nodes their position and the field
values.
and the scalar results, and then export them to a format that you can use for another application. And this is our strategy to have the more interconnection that we can have with other software. So to be able to export our data for another use in another application. So maybe we can come back to you. You can come back to me if you want to
More
start
information.
working on this script, on this capability. Yeah. We will be happy to help you on this. Yeah.
Okay, then thank you everyone. Thank you, Max. It is the end of this webinar, and see you soon on the other webinars. We were very happy to see you today. Thank
Yes,
you.
pleasure for me too. Bye-bye, everybody.
Bye-bye. Thank you.
Bye.